Accelerant provides open and containerized ransomware solutions that support an economically viable alternative to the traditional mobile telecom approach. With Accelerant's unique software architecture, we unlock the true potential of software-defined networks and network virtualization to better serve private, public, and neutral host networks. Disaggregated RAN is the solution for mastering the increasing complexity of technology and use cases towards 5G and beyond. Accelerant serves this paradigm shift as a unique and independent software provider. Cloud-native techniques bring flexibility, innovation, and scalability to radio access networks as well as hardware independence. Accelerant's unique approach to architecting its software as well as its conditional support to openly architected networks delivers true disaggregation to radio access networks. Artificial intelligence is a cornerstone of Accelerant's strategy. It drives innovation and automation in the complex challenges that mobile network operators face on a day-to-day basis. While open standards are a prerequisite to delivering truly interoperable products, integrating the individual components into a working solution remains a task cut out for our experts. Here you can see the Oran Alliance architecture and the scope of dRAX in there. You can think of dRAX as Accelerant cloud-native Open RAN platform. This cloud-native platform is deployed in Kubernetes and is all based on microservices and components that are running on a Redis NAT foundation. The dRAX SMO is an SMO which is used and implements a dashboard to show the network status, telemetry, and different statistics. The XApps are XApps that are running on top of the near real-time rig, and some of them are implemented and done by Accelerant, and others are implemented by third-party XApps. And the dRAX 5G CU itself is also based on different microservices which are architected in such a way that it enables scalability. dRAX can not only manage 5G components and an ecosystem of third-party DUs are used in 5G, but also in 4G the Accelerant small cells. So in terms of the interfaces, you can see in here how our near real-time rig and the dRAX can also interface externally to an Oran SMO and on real-time rig via netcom RESTful APIs, and how the near real-time rig itself also controls and shares data with the CU-CP and CU-UP microservices via an E2-like interface. The CU-CP, of course, they implement the standardized 3GPP NGC interface towards the 5G core and the F1 control interface towards the DU, and the CU-UP equally, it implements the NGU interface and the F1 interface towards the DU. Here you can see the CU components for the CU-CP and CU-UP, and you can identify some of the protocols that are used for this control and user plane architecture. And now we are going to see a video of Accelerant dRAX end-to-end integration with a 5G core and third-party DU and RU components.
We'll go through a brief description of the setup, then we'll fire it up and attach a phone to it, and lastly we'll try a couple of quick tests. First, we'll go through the setup we have in the lab. On the top left corner, we have a quick view of the lab setup. We have a OnePlus phone which supports 5G. This phone was placed inside a shielded box, along with a Raspberry Pi, that would be used to control the phone remotely. This setup within the shielded box would result in less interference on our wireless connection, and also it won't be interfering on other setups we have in the lab. We'd be using a B210 radio for our demo. The B210 antenna, TX and RX ports were connected to the shielded box. The B210 was also connected via USB 3 to our main server, where the L1 and the DU software were installed and would be used with the B210. In the server, we also installed our Acceleran dRAX radio intelligent controller. We also installed Acceleran CUUP and CUCP, and we made sure that the DU would be able to connect to the CU via the F1 interface. From the server, the CU was also connected via the NG interface to the core. This is going to be the setup used for the demo to make an end-to-end connection with the phone. Now let's go to the demo itself. We would SSH into the main server. A Docker Compose file would be used to start the DU. This file would contain all the radio configuration that would control the behavior of the B210, such as the frequency it would use, the PCI on the cell, or the bandwidth configured. As we can see, it's starting now and showing some information about the startup results. Acceleran dRAX includes a dashboard that we can use to monitor the setup, so let's access that. If we go to the dashboard tab on the top left corner, we can see a window with the network topology we have running now. Currently it's empty. As the DU is coming on air, we can see some information about the cell on the right. On a separate window, we are having a Wireshark trace running at the same time, showing the messages exchanged to set up the F1 interface to the DU and the NG interface to the AMF. Now we can switch off airplane mode on the phone and allow it to attach itself into the network. We can also see in the trace the RRC messages, for example. Now that the phone is connected, we can do some tests to make sure we have end-to-end connectivity. Here we are pinging Google IP from the phone, and we can see the Wireshark trace on the right showing the messages exchanged. In this last test, we will try to stream a video from YouTube. On the right side, a trace of the messages exchanged can be seen. This concluded the demo.
I'm going to describe how dRAX is integrated in 5G Records testbed with other consortium partners components. Core provides the 5G core in this testbed. The 5G core communicates with Acceleran dRAX CU using the standardized 3GPP NG interface. One of the important tasks in here is to validate the interoperability of the NG interface. Eurecom provides the DU and RU components in the testbed using an OpenAir interface implementation. The standardized interface between the CU and the DU is the F1, and one important task in here is also to validate the interoperability of this F1 interface. dRAX Technologies provides the shared access server, which is going to be providing the RF parameters and the spectrum to be used in the deployment. This shared access server communicates with a shared access client in dRAX, which is implemented also as a cloud native microservice, and which is going to be communicating with the shared access server in order to obtain the RF parameters and the spectrum to be used. Interoperability of this protocol is also very important. Once the shared access client obtains those RF parameters, it needs to configure them down into the DU and RU. And one of the most important tasks will actually be to define exactly how this configuration is going to be done with the available interfaces. And last but not least, the CU is going to be enhanced so that there are improvements for low latency and also the support of Ethernet type PDUs to support the 5G LAN feature.